When I was, does this thing work? When I was a young man, Dirac was my hero. He made a new breakthrough, a new method of doing physics, which the Guesson equation. Previous to that, Maxwell got his equations, but only in an enormous mass of gear wheels and idlers and so forth in order to understand what he was doing. But Dirac had the courage to simply guess at the form of the equation and tried to interpret it afterwards.
Yesterday, you gave us a short account of a very important development in theoretical physics that started with Einstein's special relativity, with the symmetry of space and time, and then led to a very large development which ended with another symmetry, the symmetry with the particle and antiparticle. That was the main subject, and the key word was symmetry.
Yes, that is so. I wanted to emphasize that Einstein was the first to realize the importance of symmetry. Lorentz had worked out the mathematics of the transformations. The transformations are called Lorentz transformations, but Lorentz did not realize the symmetry which was implied by these transformations. He thought that there was one frame of reference which was the good frame, the physical frame, and that other frames of reference were just mathematical fictions.
I remember the words. He introduced local time as a concept, but he said local time different from the real time.
Yes.
There he has emphasized that there is one real absolute system, the ether.
And there he was quite wrong.
Yes.
And it took him a long time, I believe until 1909, before he accepted the Einstein view.
Yes, he gave a lecture in Göttingen in 1909 or 10. And he said that perhaps we must give up the concept of equal time, of the absolute equal time, but he, I can say in German, ich würde es ungern aufgeben.
Yes. Einstein started off with a different point of view, and he showed how he was an independent thinker.
Yeah. And with the word symmetry, in this connection, you mean symmetry between time and space?
Correct, yes.
What symmetry was in the center of theoretic has changed in time. At first it was symmetry of space and time, then came other symmetries zwischen electron and anti-electron, positive and negative charge.
And then more recently, other symmetries have appeared in physics. A symmetry between proton and neutron.
Yes.
And this is only an approximate symmetry, what physicists call a broken symmetry.
Yes, but if we, I would ask you something for the former symmetry. In your work, that symmetry, space-time, showed it's important if you constructed your, what we call Dirac equation of the electron. in the days before, physicists preferred the so-called Schrödinger-Klein-Gordon Gleichung equation, but this equation has the time in a second derivative.
Yes.
And that was not acceptable for you. You have, before you had constructed what we call transformation theory. And there you needed the concept of probability and the first derivative.
That is correct, yes, yes. And that forced me into a different kind of equation. And this different equation brings in the spin of the electron. It was very unexpected to me to see the spin appearing in this way.
A spin, that means a moment of momentum and magnetic moment, both together.
They both come together.
Yes.
I thought one would first get a satisfactory theory of a particle without spin, and then one would proceed to a more complicated theory of the particle with spin.
Yes.
But it turned out differently. The simplest kind of particle does have a spin.
Yes. You mean perhaps Pauli Weisskopf with the scalar theory, and physicists saw that they can incorporate any spin into a consequent theory, but it is quite more complicated.
Yes.
I agree.
Yes.
The simplest particle that could exist was the fermion with a spin 1/2, the electron.
That is so, yes, yes. It was a great revelation when this appeared. And then, with the solution of these difficulties, one was able to concentrate on the one remaining difficulty, how one should deal with the negative energy states. And it took quite a while, perhaps a year, to understand that, and to bring in the concept of a vacuum in which all the negative energy states are occupied.
Is it possible to express it in the following manner? In this theory of the electron, let me say the Dirac theory, you can treat pairs of particles, positrons, electrons, in the form of a one-particle theory. But if you have scalar spin, scalar particles, or a Pauli Weisskopf theory, you can treat pairs, and only in the form of a many-body theory.
Yes, yes, that is so, yes. Should we speak a little about general relativity?
Yes.
General relativity was considered by Einstein as his most important discovery. He was working entirely alone on the new mathematical ideas, and it was a big triumph for him to be able to get his ideas straightened out and to introduce a new theory of gravitation, bringing in a very powerful kind of symmetry. This symmetry is of importance in physics only where gravitational fields occur, while the symmetry previously, the symmetry of special relativity, is of importance in all physics. So that this further symmetry introduced by general relativity, although it is such a wonderful mathematical theory, does not have the big effect on physics. And I might say that my recent work has been very much concerned with Einstein's general relativity. And I believe that the times and distances which are to be used in Einstein's general relativity are not the same as the times and distances which would be provided by atomic clocks. There are good theoretical reasons for believing that that is so, and for believing that gravitational forces are getting weaker compared to electric forces.
I feel very honored to, and I had to accept, after all, since he was my hero all the time, and I think it's kind of wonderful to have discovered myself giving a lecture in his honor. He was the first to, as he said, wed quantum mechanics and relativity together in his relativistic equation for the electron. At first he thought that it was necessary, the spin that you had to have was necessary, and that spin was a consequence of relativity. He also invented some ideas called Zitterbewegung and other things which turned out not to be very useful in the interpretation of the equation. But after some time, with the puzzle of the negative energies, he finally solved by filling them all up and making bubbles, which predicted the existence of antiparticles. And then it was realized that the idea that was necessary to wed quantum mechanics and relativity together was the existence of antiparticles. When that was added, you could do it with any spin, as Pauli and Weishaupt proved, and therefore I want to start the other way about and start with the antiparticles and try to explain why there must be antiparticles if you try to put quantum mechanics with relativity. It also permits us to solve another problem which is very mysterious pre-relativistic times. One of the grand mysteries of the world is the Pauli exclusion principle, that when you exchange two particles, you should put in a minus sign. It is easy to demonstrate that in non-relativistic mechanics, if nature started that way, it'll be that way all the time. And so the problem would be pushed back to creation, and God knows how that was done. But with the existence of antiparticles, we make new pairs and therefore new electrons. And the mystery now is, why does the new electron that has just been made have to be antisymmetric with respect to the others and can't get into the same state as the others that are already there? And therefore, the existence of particles and antiparticles permits us to ask the question in a practical way. Suppose I make two new pairs with two electrons and I compare the amplitudes for when they annihilate directly or when they exchange before they annihilate. Why? Is there a minus sign? All these things have been solved a long time ago in a beautiful way, in fact, the simplest way, in the spirit of Dirac, with lots of symbols and operators and so on. And I'm going backwards to Maxwell's gear wheels, and I'm going to try to tell you as best I can what I think is a way of looking at these things so that they appear not so mysterious. I am adding nothing to what is known before, it's only exposition. So, here we go as to how things work, why there must be antiparticles.